Welcome, physicists, to the culmination of everything that we've been talking about so far in regards to the electric force, the electric current, and the potential between electric sources. Electric circuits. In order to discuss electric circuits, though, we first have to discuss electric cells. What is a cell? A cell is a device that uses a chemical reaction to generate electricity. Uses a chemical reaction to generate electricity. Now, if you think about it, chemical energy is actually just electric potential, because the way chemical energy works is chemical energy is the energy stored in the bonds. Like, let's look at H2O. There's the O. It's stored in these bonds here. The energy stored in the bonds. And those bonds are just electrons and protons of the atoms arranged in such a way that they won't spontaneously explode and fly apart. They're stable. That's electric potential energy. So what a chemical reaction happens, they break. And then they reform with less potential energy than they did before, more stable. There's less energy built up in those bonds. And that is the essence of a battery. That extra lost electrical energy is sent through a circuit, or in the case of a simple cell, as we will discuss right now, it just kind of hangs out. Now, the simple cell is just a solution of acid with two metal bars dunked in it, one made of copper and one made of zinc. Now, what happens is that both the copper and the zinc start to dissolve in the acid. Copper starts to dissolve into copper 2+, zinc starts to dissolve into zinc 2+ ions. You'll notice that the charge goes up from a zero charge, as all base elements have, to a positive charge of an ion. So some of the electrons are left behind as the zinc and copper dissolve. However, on the activity series of elements, which you don't have to know, this is just arbitrary, zinc is more reactive than copper. So zinc reacts quickly and therefore has a lot more electrons than copper. And that creates a potential difference. Copper here ends up having a higher potential difference than zinc. A higher potential than zinc, which creates a potential difference across them. As you know, the electrons will end up moving from the low potential difference to the high potential difference. They're going to move across, right? Yeah. And so that is your simple cell. There is a current created where electrons start jumping ship from the zinc because it's way too negative and going over to copper because it's less negative. Now in a typical cell, your typical cell is your battery, right? We talk about ends being positive and negative, but in the simple cell, and as can be in many cells, both ends can be negative. The key difference here is the fact that there's a difference in potentials between either end, between the anode and the cathode. Now, if you want a more detailed explanation of how the simple cell works and how it goes up into voltaic and electrolytic cells, head over to our chemistry videos, where we'll discuss that in our redox section. But this is about the most in-depth definition you'll get of the simple cell for now, because we are going to discuss what that means. The symbol for a cell, when you're drawing circuit diagrams, looks like that. The longer stick is the area of high potential, and the lower stick is the area of low potential. And as I said before, the electrons are going to want to jump ship from high to low, right? And that creates a potential difference. Just for the purposes of, just to make things easy, we always take the low side to be equal to 0 and the high side to be 1, so the potential difference ends up equaling 1 volt between either end here. However, unfortunately, we do not live in an ideal world, and as the electrons jump ship through the acid or whatever is going to be in your cell, the components of the cell are going to have some internal resistance. So we're going to have to put a resistor there. The symbol for a resistor in a circuit is just a little block. And that represents the internal resistance of the cell. And so that means that some of the energy is lost over the course of the jumping over this way. Now we have a new term to define, and that new term is EMF, as represented by the Greek letter epsilon. And the EMF is very similar to potential difference, but is different in a few key ways. It is the work done per unit charge, taking the charges from from the low potential to the high potential. You notice how that definition is kind of weird? Because we just said that the electrons are going to want to, well, no, that's not really weird. The electrons, oh, I drew that wrong, sorry. They're going to want to jump from the low potential to the high potential, from the zinc to the copper. Terribly sorry about that. But yeah, so the EMF is simply the work done to take the electrons from here over to there. However, this is different from the potential difference of the cell itself, because as we've already discussed, there's an internal resistance in the cell that causes the PD to lower. However, when we're talking about EMF, we're going to talk about EMF in terms of cells. And EMF in terms of cells is going to not account for that internal resistance. So more often than not, the potential difference of your cell is going to be less than your EMF. However, if there's no current flowing, then your potential difference is going to be equal to your EMF because you don't have to account for that resistance. And that is called terminal potential difference because there's no current, it's terminal. It's a dead cell. Now, there's another thing we can discuss when it comes to the idea of EMFs. And that is, what if you did not attach the simple circuit here to a cell? Well, all the electrons would rush over to the area of higher potential. And they just kind of hang out there, right? Then what if you suddenly connected it to a circuit, right? Well, then all of the electrons would suddenly be moving from the high potential to the low potential. And they keep on moving from the high potential to the low potential. And they keep on moving from the high potential to the low potential, which, as you may have noticed, is different from our basic cell where it moves from low to high, right? And that is defined as a discharge, where the electrons are built up over at copper, and once connected to a circuit, they just all want to get out. It's a rush of electricity. That's the discharge of a cell. So now we're going to discuss circuits. Finally, now that we've covered cells. And the simplest circuit is defined as one cell connected to one resistor. Now, this resistor is different than the internal resistor. This resistor is completely separate from the cell. And a resistor is anything that converts the electrical energy, right, that is traveling through the circuit to some other form of energy, more often than not, heat energy. So your typical resistor that you might see like in a circuit building set will look like this. It'll have a zebra stripes on it. It'll tell you what the resistance is based on a code. But in a real circuit that's practical and used in real life, if you have a light bulb, that would be considered a resistor. If you connected it to an engine, maybe, that would be considered a resistor. Anything that converts that electrical energy out into something else. Now, if we're talking about the cell is going to have an EMF, right? And the resistor itself, because it is converting that, it's going to have a resistance. And because it's converting the energy out, it's going to have a potential difference. Now, because of conservation of energy, the amount of chemical energy converted to electrical energy, which is another definition of EMF, a simpler definition of EMF, is the amount of chemical energy converted to electrical energy. Right? And we're assuming that no energy is lost in the circuit until we get to the resistor. And the resistor is going to convert that electrical energy to heat. So the potential difference of the resistor is going to be the amount of electric energy converted to, for simple purposes, heat energy. And because of law of conservation of energy, in this simple circuit, the EMF is going to equal the potential difference of that one resistor. And because we know Ohm's law, potential difference equals current times resistance, then the EMF is also going to equal current times resistance, which is an easy way to calculate the cell. And the current, of course, is going to be the current that travels through the circuit, which won't be traveling that way. It'll be traveling this way. Because in a current, I forgot to mention that, in a current, instead of traveling from low to high directly, it's going to travel from high to low. It's going to travel around like this, because what happens is you've got a high potential here, right? And it goes all the way over, and it loses some, and it comes out with a lower potential, and it goes back up over here, where it then goes again the direction it wants to go, from high to low. It's a circle, goes around. That's how a circuit works. However, that is the simplest circuit. Now we're going to start talking about not so simple circuits, because not all circuits, unfortunately, are that simple. We didn't account for the internal resistance of the cell. So what if we account for the internal resistance of the cell? Draw. We put a little resistor off to the side. We're going to label it with little r. And then we've got the other resistor that we were using before, which we'll label with big R. Well then, how do we calculate the EMF here? Well, a nice little thing to know about resistors is that the total potential difference, the amount of electric energy converted to heat energy for both of these resistors, will equal the EMF. So, we know that the current that flows through them multiplied by the resistance will give us the potential difference according to Ohm's law. So the EMF is going to equal the current, because the current is constant, times the big R, plus the current times the little r. If you rearrange this, the way to find the current in any cell is the EMF in any circuit is the EMF of the cell in the circuit over one resistor plus the other resistor. Remember this formula? It will come in use later. But first we're going to talk about electrical power. And power, as you may remember from back in our mechanics, is the rate at which energy is changed. Because if you remember, the old formula for power is work over time. And work is a change in energy. So, energy is changed, the rate. Over time, it's a rate. Now, there are two ways that we can measure power. The first of which is power delivered. Power delivered from the battery or the cell into the circuit. And that is going to be the amount of chemical energy converted to electrical energy. Well, how do we calculate that? Well, we know that the amount of chemical energy converted to electrical energy already, we know that's the EMF, right? Yeah. And we know that for a given charge, if we multiply the EMF times the charge that is being transferred, right, that will end up giving us the total amount of energy. The total amount of charges multiplied by how they are changed from chemical to electrical. And then because it's a rate, it's the rate at which energy is changed, we put that over time. What's charge over time? That's current. So the power delivered is equal to the EMF multiplied by the current. And then we have power dissipated, which is equal to the amount of electrical energy converted to heat. And like I already told you, that's the potential difference, the combined potential difference of the resistors, which we represent with V. And so, same concept, V times Q is going to be that total amount of energy, because if you remember, the potential energy equals the potential difference times the charge. Same concept is up there. And then as a rate over T, Q over T is current, so the power dissipated equals the potential difference of all the resistors multiplied by the current. Now that is a useful equation right there, because you can go and combine that with Ohm's law and rearrange it to get other formulas. Say for instance we know P equals VI, but we also know that V equals IR, so if we went and we inserted IR for V, now we know that P equals I squared R, if we didn't have the potential difference but we had the resistance. And then if we rearrange that for the same formula, we know that I equals V over R, so if we inserted that for I, we would know that P equals V squared over R if we just had the potential difference in the resistance. So that kind of completes the Ohm's law cycle there. So you can calculate power, current, resistance, or potential difference all using Ohm's nice little law. And that's pretty great, I do think myself. Now, that's circuits right there. I mean, like I said, resistors can be, it could be like a water boiler, a light bulb, electric motor, anything that converts your electrical energy to heat energy. And those are circuits. But what, I ask, my dear physicist, do you do when you have multiple resistors? Well, let me explain it to you. Oh yeah, first, power is measured in watts, just in case you wanted a unit for that. But multiple resistors. What if you had two resistors in series? Right? Well, the current across the entirety of the resistors is going to be constant, right? You know the current is going to be constant. And fortunately enough, when you've got potential difference 1 and potential difference 2, and they're in series, you add them up. V1 plus V2 equals your V total, right? Well, if we apply Ohm's law, we know V equals IR, and I is constant, so IR1 plus IR2 equals IR total. We divide everything by I, and when you have resistors in series, you just add them up to get your total resistance. It's pretty simple. But what if you were doing that in parallel? What does in parallel mean? Well, that means your wire splits. You got a junction. And then you got a resistor on either junction, and then it rejoins. Well, the thing is, the current in is going to be the same as the current out, because current is always conserved, just like charge is always conserved, right? So that means that this is going to be 1. That means this is going to be, if we're considering this current 1, this current 2, I1 plus I2 is going to equal I total, right? Right. Yeah. So we know that current equals voltage over resistance. So that means voltage over resistance total equals voltage over resistance 1 plus voltage over resistance 2. And voltage, thankfully enough, is constant throughout. The voltages will just add up to equal the total voltage, just like they did in series. But for resistances, now we've got a new formula. If your resistors are in parallel, you're going to need 1 over R total equals 1 over R1 plus 1 over R2 to get your total resistance in parallel. And those are two formulas to help you solve for resistance if you're ever given a circuit problem that wants you to solve for resistance. Moving on, what if you put your cells in series? That's right, what if you have two cells? Well, if you have two cells in series, it's pretty simple. The EMF of the first one plus the EMF of the second one equals your total EMF. Simple, straightforward. But what if you had two cells in parallel? That's where things start to get complicated. Not too complicated enough if the EMFs are equal. If the EMF equals 1 volt here and the EMF equals 1 volt here, then the total is going to be 1 volt. It's going to be like there's just one cell there. However, if they're different voltages, well, there's no real way to actually determine what the one will be because you have to account for the internal resistances here of each of the cell. Because having different EMFs just doesn't make sense without internal resistance. You have the current going up, and then it gets a lot of chemical energy converted to electrical energy here, right? But then not so much here. And that means the current in is not going to equal the current out, which that's not true. It can't be true. So what you have to account for is for the resistance. The resistance is going to take away some of the energy here and make this equal. And because this resistance is smaller, it's not going to do quite as much, so it's just going to end up equaling out in the end. But still, I mean, that's really not important. They're probably not going to give you a problem where they ask you to calculate two cells in parallel. It's just a bit too complicated. Now, how do we measure our voltages and our currents? Well, the reason we're covering this is because it's actually quite a complicated process. You measure potential difference with a voltmeter. And the way you do the voltmeter is, say you want to calculate the potential difference from point A to B. You put one node at point A, you put the other node at point B, and the nodes connect to our buddy the voltmeter, and they've got to be connected in parallel. Why? Because you want to minimize the current. Because V equals IR, right? So if you have a big current, it's going to make your potential difference appear larger than it actually is. And that is why your voltmeter here ideally wants to have an infinite resistance so it can repel all that current, because things with high resistance don't allow a good current, right? Right. Now what if you wanted to measure your current? You measure that with an ammeter. Now the ammeter, you're going to break your circuit, connect one node there, connect another node there, and connect your buddy the ammeter in series. Now for the same reason as over here we have infinite resistance, we want to have ideally zero resistance in the ammeter because we don't want any of the current to be resisted. So we can measure the current exactly. And of course this one's going to give it in volts and this one's going to give it in amperes. And that's pretty simple when it comes to that. Now, all the stuff we've talked about so far can be summed up with three simple laws. The first one we've already discussed. Ohm's law, which is simply potential difference equals current times resistance. That'll help you solve a lot of circuit problems. If you just have resistance or current, or just have resistance and potential difference, or just have potential difference in current, you can use that to solve anything. Two, when you're talking about cells and resistors, we've got Kirchhoff's first law, which, when we're talking about resistors in series and when your current splits, current into a junction equals the current out of a junction. Pretty simple law. And the final one, Kirchhoff's second law, is the one I discussed a bit early on when I said the amount of chemical energy converted to electrical energy has to equal the amount of electrical energy converted to heat energy, which is that the EMF of the battery has to equal the total potential differences of all the resistors. And using these three laws, you put them in a box because they're really important, you can solve pretty much any circuit problem that any IB test has to throw at you. Except the weird ones, which we're going to discuss right now. There are two weird, unique sort of cases when it comes to circuit problems. The first of which being the potential divider. And the whole diggity deal with the potential divider is you've got your cell, it connects to one resistor, it connects to another resistor. But around your second resistor here, you've got this thing. That's your potential divider. It just wants the voltage of this specific resistor. So, if you think the EMF here is going to give a potential difference across the entire circuit of Vn. That's what we're going to label it, Vn. So we know that the EMF equals Vn. We know from Ohm's law that the current in the circuit is going to equal I equals over VR. And the total resistance, because they're in series, is just going to be R1 plus R2, right? So calculating that, we know the current in the circuit is going to be V over R1 plus R2, like we calculated earlier when we were talking about the internal resistance and stuff, right? However, V out is just applying to, this is V out, it's just applying to that one resistor there, R2. So the V out is going to equal the current, which is constant, multiplied only by R2. Then we solve for current equals V out over R2. And then we equate the two equations, and we end up getting the potential divider formula, which is that your V out is going to equal your V in multiplied by your R2 over R1 plus R2. And that is simply to calculate the potential difference in one specific resistor. That's the potential divider. The other unique case is the variable resistor. Now, if you remember from way back when, resistance is equal to resistivity times times the length over the cross-sectional area, right? Right. Well, that means if you increase the length of the wire that connects into your resistor, right, from little shorty to big guy, the resistance in that wire is going to increase. And that's the idea behind the potential divider. And if the resistance increases, so does the potential difference. So say you have a cell connecting to a circuit. You've got your resistor here, and it's of a certain length, and you've got your potential divider to determine just how much, and you say it's 0 volts when it's this small, right? But then you go and you increase the length here, right? And that increases your resistance, which increases your potential difference, which gives you now 0.5 volts. And that is called a potentiometer, which is the whole idea behind dimming switches. What happens here is this is called a sliding resistor, and when you move the dim switch up, it slides out the resistor to make it longer, and it gives you more potential difference, which means that more electric energy is converted to heat and light energy, which means that your lights give off more light. And then when you slide it down to dim it, it gets shortened, and your lights start giving off less light until they give off no light at all. And that's the whole idea there behind the variable resistor. And those are really the only unique cases there. So that's it. That's all we have to discuss about electricity. We're almost done with this section. Join us next time for magnetism.